Hello and welcome to Unit 2, Part 3, Enzymes, Day 3. And this is the end of Unit 2. The only thing we have left are 2 more labs, and then we're going to be taking our exam. So let's go ahead and begin. All right, so today's aim is how does pH affect enzyme activity? And we've been talking about enzymes for a little bit now. So hopefully there are some things that we remember about enzymes and that we'll notate on our papers. So enzymes are biological catalysts. And we remember that they're biological catalysts because enzymes are protein, baby. And we know that these proteins are made of organic compounds. Enzymes are synthesized in the ribosome. All these things are things that we should think of when we see enzymes. But this here is a new term that we're going to talk about for the first time today, pH. And we're also going to talk more about pH when we do a lab tomorrow. So what is pH is going to be one of the questions that we're going to answer with today's notes. So this first set of questions, I want you guys to look at on your own. So I am about to go over them, but I would like you to pause the video right now and try and answer the do now questions 1, 2, and 3 on your own, and then play the video again for me to go over it, okay? Because it involves you interpreting the graph. So please press pause on your video. And we're back. Okay, so the do now asks, use the graphs below to answer the following questions. What is the ideal temperature for the enzyme in graph A? So this word ideal, you might also see a different word in questions like this, optimum. And in both cases, what we're talking about is the best. So what is the best temperature for the enzyme in graph A? So we can see here on the y-axis, we're looking at the rate of enzyme activity. So at which temperature is the rate of enzyme activity, which is going to be the best, right? It's going to be the highest breakdown of substrate or synthesis of substrate is going to occur at the peak of the graph, right? And best means peak, and you can see the peak of the graph. So what temperature is that? Approximately 35 degrees Celsius. What is the ideal pH for the enzyme in graph B? So now we were just talking about temperature, something that we're familiar with. And temperature and pH, as you may recall from Enzymes Day 2, are 2 factors that influence the rate of enzyme activity. So what is the ideal pH for enzyme in graph B? So we're taking a look. Bye, guys.
Sorry.
No.
Oh, sorry.
Okay, I'm filming. I'll talk to you later. Sorry. Bye-bye. So that was just Mr. Sterling, who you may remember from the food nutrient analysis video. But now let's go ahead and return to what is the ideal pH for the enzyme in graph B. So we can see again, peak point in the graph, right up here, is about 7.5 to 8. And these two numbers, a pH of 7 and the temperature of 35 degrees Celsius, these are very typical ideal temperatures and ideal pHs for enzyme activity because 7 is the pH of water. So this is approximately neutral. And 35 degrees is a typical, comfortable, warm day, just a little bit below body temperature, which is an ideal temperature. Like, you might imagine yourself being happy in that temperature, so would enzymes. So just like people do best at a certain temperature, right? Like some people it's a little higher, some people it's a little lower. Enzymes are the same way. Some enzymes like really, really high pH, some enzymes like really, really low pH. Some enzymes are right in the middle. It depends upon where they function in the body and what they actually do, what they break down. So number 3 says, imagine that the enzyme in graph B is placed in a new environment with a pH value of 3. Using graph B, describe how this enzyme will function. So it's placed in a new environment with a pH value of 3. And we can see here at the pH of 3, we have almost no enzyme activity. So we can say this enzyme will not function at such a low acidic, we're about to talk about that, pH, right? So you can see here the enzyme will not function at that pH. It's barely doing anything. So at that point, the reaction may not occur, or it would occur at a much slower rate than it would in the appropriate pH. All right, let us continue. Now, introduction to pH. What the heck is this pH stuff we've been going on about? So, even though you've never set foot in chemistry, chances are you know a thing or two about acids and bases. For instance, have you drank orange juice or soda? If so, you know some common acidic solutions. So orange juice and soda, and I'm gonna mark those with red. We'll see why in a moment. Oops. Orange juice and soda are both, wow, fail. Orange juice, there we go, and soda are both acids. And if you've ever used baking soda or egg whites while cooking, then you're familiar with some bases as well. And let's go ahead and denote that with blue. Baking soda or egg whites, bases. You may have noticed that acidic things tend to taste sour, or that some basic things like soap, so soap is also basic, tend to be slippery. But what does it actually mean for something to be acidic or basic? To give you the short answer, so like this coffee that I have here is very acidic. Something else that is acidic is vinegar. We're about to go through many examples, but in general, things that are acidic have a high concentration of hydrogen ions, greater than that of pure water. So they're going to be below that number 7, which is the neutral pH, which is the pH of water. And again, pH stands for the concentration of hydrogen ions. So we're talking about a high concentration of hydrogen ions or a low concentration of hydrogen ions. And what that abbreviation stands for, the reason that the P is always lowercase and H is uppercase, is because we're talking about the potential. So the potential, which is theoretical. So potential could mean either high or low, right? Potential for hydrogen. And specifically, not just hydrogen, but H+, which means it's a positive hydrogen ion, which means that its net charge is positive. So we are not going to get so involved in the chemistry of pH, but you want to at least understand that we're talking about hydrogen ions. So these are not neutral atoms, they're ions that are charged. And that's why it affects the chemical composition of the liquid. That's why pH is an important factor when we talk about different liquids, and it's especially an important factor when we talk about your internal environment in your body and in the internal environment of all living things. So again, an acidic solution has a high concentration of hydrogen ions, greater than that of pure water. And interestingly enough, the high concentration of hydrogen ions means you're going to be low on the pH scale. So something that is acidic is going to be from 1 to 6 or even below 1 to 6. So like not 0, but like 0.1 to 6 is acidic. 7 is neutral. And let's say even, we're going to be more specific. 0.1 to 6.9 is acidic. 7 is neutral. And then basic is going to be 7.1 to 14. And that's our scale. So the pH scale is used to rank solutions in terms of acidity or basicity. And it ranges from 0 to 14. Anything below 7 is acidic, and anything above 7 is basic or alkaline. And that word alkaline means the same thing as basic. So acid is usually a word that we encounter because we consume a lot of acids. So things like lemon juice and coffee, these things are acidic, and we eat them. And it's fine for us to eat things that are acidic. Vinegar is acidic, like spicy food is acidic. We eat lots of acidic things. But if you look at stuff that is basic, a lot less of that is edible. So in general, something that is very acidic or very basic, either way, is going to be harmful for you to consume, but we tend to hang out a little bit more on the acidic side of things when we eat. All right. So if we were doing this in class, I would have you guys discuss this together. So let's spend a moment and chat about this scale. So you have your blood here, which is just slightly basic. Excuse me. So the blood, just slightly basic. So right there, 7.4. And the cytoplasm of our cells, which is just slightly acidic, but they're right there in that neutral zone, right? Which is why we need a lot of water in our diets. Water is really important for us for many reasons, but also because it helps keep our cells hydrated and maintain that almost neutral pH. So we have up here, your options. So we're going to be ranking. We're going to be listing, it's kind of like ranking, a couple different solutions. So they're missing on your paper. The solutions we're going to be ranking are urine, bleach. I'm going to do like a Dora the Explorer type thing, okay? So urine, bleach. I already told you about black coffee. So again, you're going to be ranking these solutions based on this scale, which we said down here on the low end is acidic, and up here on the high end is basic or alkaline. So like batteries, alkaline batteries, usually we talk about battery acid, but in the case of alkaline batteries, they're basic. Okay, black coffee, seawater, and gastric acid. And I will give you a hint regarding seawater. So if you think about the ocean, I assume at least some of you have been swimming in the ocean. And you think about like soapy water. If you've ever even like been washing some potatoes in the sink with some salt, You know, like you're about to prepare some like mashed potatoes, you're peeling the potatoes, but they got a little salt on them. What does salt do to the water? And if you're at home right now and you have some salt and some water and you're feeling extra experimental, go ahead and put some salt and some water together, even some soapy water, and compare those things. How does salt water versus soapy water make your hands feel? And I'll just turn you up here. Some basic things, like soap, tend to be slippery. All right, and the last thing that you're going to rank is stomach acid. And that name should give you a clue as far as where it winds up on the scale. And we're going to be filling in these 1, 2, 3, 4, 5 blanks with 1, 2, 3, 4, 5 answers. So like Dora the Explorer, pause your video, fill these in, and then press play. All right, did you figure it out? Let's talk about it. So over here at the top end of the scale, we have, for most basic, the one that you definitely do not want to drink, even if the President of the United States tells you it might help you cure COVID. We're talking about bleach, folks. Do not drink bleach. Bleach is extremely basic. So bleach is extremely different from the composition of our bodies. It is all the way there at the top of the basicity scale. And I don't recommend that you do this, so please don't do this. But if any of you have ever touched bleach liquid, so you've been cleaning, maybe like scrubbing the shower or something, which you should always use gloves when using bleach, especially if it's undiluted, and this would be undiluted bleach. It is extremely basic and it is slippery. So like if you're ever like using Clorox wipes even, you might notice that that liquid is slippery. It's because that liquid is extremely basic. And then just under bleach, we have soapy water. So again, soap is extremely toxic for us to drink, but it is very good at cleaning things. Then just below soapy water, we have ammonia solution, which is also something that's used to clean. It's also a compound that's found in really high concentration in cat urine. So cat urine is quite basic. We have milk of magnesia. Milk of magnesia is interesting because this is really the only one of these things that we would eat in isolation. And milk of magnesia is, you may have seen it under the name Phillips at the store, but milk of magnesia is something that you drink if you have a sick, upset stomach. So milk of magnesia is medicine, and it is extremely basic or quite basic. That we have baking food, but we wouldn't usually eat baking soda on its own. Although if any of you have ever brushed your teeth with baking soda, you know that baking soda is slippery, and baking soda is similar to chemical compounds like soap and bleach and ammonia, and that baking soda is good at getting different chemical compounds to separate or cause a breakdown. So it is basic enough to cause a breakdown. Then as we get closer to a more neutral pH, let's go ahead and cross bleach off our list. As we get closer to a more neutral pH, the next on our list is seawater. Seawater. So as I gave you a little clue, salt water or seawater is quite slippery, and it is basic because of all of the salt in the water that changes the chemical composition of the water itself, and it doesn't allow the additional like free hydrogen ions to be loose in the water like they would be in neutral water, which causes slightly lower the neutral pH. Seawater has a slightly higher or basic pH, and really, again, this is much more complicated when we talk about it from a chemistry perspective, but this is about as deep as we need to go in living environment. We just need to understand how these liquids with different pHs, or how these solutions, and let's actually like define that word here. So when we're talking about all these different liquids, there are solutions. And we're going to talk about either acidic or basic solutions. And in this case, seawater is a basic solution. And then right under seawater, we have our blood, which is just slightly basic. Below that, we have 7, which is neutral, which is drinking water. Drinking water, got to get that neutral pH in. And then just below that, just slightly acidic, we have the cytoplasm of our cells. All right, and then just below distilled water, getting more acidic now. A little bit more acidic now. A little bit more acidic now. We have 3 different liquids left. We have black coffee, we have stomach acid, and we have our urine. And hopefully these body fluids listed here nearby gave you a clue that next we're talking about our urine. We're going to talk more about urine and what actually makes up urine when we get into the excretory system in Unit 5. But urine is just slightly acidic because of the addition of urea. So that's like the waste that is broken down in our bodies. And that waste is what colors our urine. And that waste makes the liquid that we excrete just slightly acidic. But you can see just slightly acidic there, right? At a 6. Next, we have, so now, here I'm drinking black coffee. Scout's honor, no milk in there or nothing. So do you think that black coffee is a 1 on the acidic scale? Below lemon juice. If anyone has ever tasted lemon juice versus tasted black coffee, you can attest. Black coffee is less caustic, which is a synonym for corrosive, which is another synonym for like acidic and damaging. Getting those science vocab words in today. But ladies and gentlemen, black coffee, can you believe it, is less acidic than tomato juice? It's kind of surprising to me, but you know, it is science. And then we have, last but not least, gastric acid or our stomach acid. This word gastric just means like gastrointestinal, your stomach. And our stomach acid is extremely acidic. So what happens in your stomach? Digestion. And what are we talking about? We're talking about enzymes that are very important to chemical reactions, such as digestion. And so pH affects the rate of enzyme action. It is a factor that influences enzyme action, but also solutions with very high or very low pH can themselves help break down certain chemical compounds. So when we talk about our stomach, it makes sense that the environment in our stomach is extremely acidic, because when substances enter our stomach, we want them to be broken down quickly. We want them to be broken down and digested, so that way the tiny little constituent parts can get small enough so that they can enter our bloodstream and provide us with the nutrients that we need to keep on living life. Oh, forgive me. Those were on your papers. They just weren't on mine. All right, so now let's go on to part B and talk about enzymes and pH. Enzymes work best within specific temperature and pH ranges, and suboptimal conditions can cause an enzyme to lose its ability to bind to a substrate. So suboptimal conditions, meaning either too high or too low pH. So those were the points in the graph where it wasn't peaked, right? Are suboptimal. Each enzyme has an optimum or best pH range. Changing the pH outside of this range will slow enzyme activity. Extreme pH values can cause enzymes to denature. So here's a normal enzyme, and it's either too hot or too acidic or too basic of a pH, and what happened to the enzyme when it's denatured. So this means it broke down. And ooh, that is a little messy. But remember that something that is extremely important for an enzyme is its shape, right? The way an enzyme fits with the substrate is by its shape. It's broken down. So you can see the denatured enzyme has had its shape fundamentally altered. So it's no longer going to fit in like a lock and key with the substrate. And as a result, that denatured enzyme is like kaputnik, no more enzyme. So recall, what is a substrate? The substrate is what binds to the enzyme. So it is a molecule that is acted upon or broken down by an enzyme. So in this case, let's draw in our substrate. That's not going to fit in there. See, I'm sure you guys could draw a better substrate than I could. Those of you that use a molecule that is acted upon or broken down by an enzyme. And remember that it fits in, and it's smaller than the enzyme, but it fits right into its little hole, and that's about the best I can do. But you can see the substrate is a specific shape, and remember the enzymes themselves are specific. So we have thousands of different enzymes to accommodate all the different chemical reactions that occur in our bodies. And once the enzyme becomes denatured, once it changes, it's no longer able to do its job. So we might need to make a new enzyme. So substrate is the molecule that is acted upon or broken down by an enzyme. So now denature, well, I already told you, but based on the clue in the image, you can surmise that denature means to break down or damage. And there's two blanks here because typically in class, you come up with a definition for denature and then we give you the real definition, but they're both the same. I do believe you guys have already watched this Meme Sisters video on enzymes, or at least I hope you have. But if you haven't, that would be a very useful review. And don't forget to go and do your exit ticket. Tomorrow, we're going to be doing a very exciting lab on pH. And we're going to discuss how different fluids have different pHs and how we actually calculate or measure pH. So today's aim was, how does pH affect enzyme activity? And we went through all these practice problems here. Don't forget to please like and subscribe to my channel. Also to go and complete your exit ticket. And I'll see you all tomorrow on Zoom. Bye guys, have a great day.